right, so we started lecturing last time. We started talking about chapter 1, which wasn't too much going on there, but we got into sort of chapter 2. And in chapter 2, we talked about sort of measurements a little bit. And more importantly, we talked about units. And as we talked about, it's really important to always, when you take a measurement, you should have a number and a unit. And as we talked about, it gives people a reference as to what that number represents. So you should never, ever have just numbers. Make sure you always include the units. We talked really about two types of units. There's sort of the English units that we kind of use. And then there's really the metric system that pretty much, again, everybody else sort of uses. And we talked about sort of in chemistry and science, they sort of came together and created a standard system of units, which is referred to again as the SI system of units. It really is sort of based off of the metric system. And we talked a little bit about some of the prefixes that are used to kind of convert some of those metric systems. Remember again that if kilo is 10 to the 3, that is, for example, how many in one of the prefix unit there is to the base unit. So in 1 kilogram, which is the prefix unit, there would be 10 to the 3 grams, or 1 times 10 to the 3, which is in scientific notation. Remember, people always sort of get those things backwards when they go to use it. We also talked about 3 types of temperature, which is degrees Celsius, degrees Fahrenheit, and Kelvin. And as we talked about, that is pretty much going to be the major one that we use the most in chemistry. And Celsius and Fahrenheit, not too much, but if you want the temperature in Fahrenheit, it is 1.8 times the temperature in Celsius plus a 32. If you want the temperature in Celsius, it's the temperature in Fahrenheit minus 32 divided by 1.8. The one that we use the most really is converting to Kelvin. Temperature in Kelvin is the temperature in Celsius plus our 273. As we talked about, the real number is 273.15, but most people don't use that 0.15, so we will use 273. And use a little bit more than some others is our temperature in Celsius from Kelvin, which means we would just subtract the 273 in that case. Out of all those, and outside of chapter 2, probably that is the one you're going to use the most. As we also have talked about a number of times, they do want you to know all these things. So again, you do need to know these formulas and other formulas, as they will not be provided for you. We also talked a little bit about significant figures in terms of specifically for temperature conversions. And when you are, again, doing simply a temperature to temperature conversion, you are not doing anything else with it and just basically just changing the temperature unit. We use a general rule for significant figures, which is whatever our original number looked like, that is what your converted number should look like. So if your original temperature number was a whole number, when you convert it, it should be a whole number. If it went to like the second decimal place, you should take it to the second decimal place and so forth. Again, that is the specific rules, not for significant figures in general, but specifically for only temperature to temperature sort of conversion. We finished up, I think, talking about scientific notation. Which is n times 10 to the n. Once again, that is a number between 1 and 10. Again, not 10, 100, 20 or anything like that, and not like a point something number. It doesn't need to be 1 is okay, but not 10. So it doesn't need to be a number between there. And that times 10 to the n is either a positive or negative number, again, depending on which way you're moving the decimal point to get to a number between 1 and 10. More importantly, what we talked about at the very end, I think last time, is to how to properly punch these things into your calculator. Remember that you should have exponent buttons, which is either a EE button, an EXP button, or maybe times 10 to the n, which usually has like a little wheel with it. Remember that when you use something like that, like 6.25 times 10 to the minus 1, you would hit 6.25, you would hit your exponent button. When you hit the exponent button, it represents the times 10 part of the number, so you shouldn't hit multiplication button or anything like that. So you should just put 6.25. It might pop an E, which represents the times 10 part, or it may go something like this, maybe put up a couple of zeros. And then there's also negative buttons on your calculator, which is this or this, again, not the subtract button. And you would use something like the negative button and 1, and it'll make that -1, make that -1. So you want to make sure that you always use your exponent button. If you're not using your exponent button, you usually will find that that the number looks pretty good, the answer, except the exponent part's off by like 1 or so. And that's usually an indication that you're not punching it in correctly. Remember, though, if you do have sort of this combination of buttons, the only different thing that you need to do is you got to parenthesis up everybody, each number that's in scientific notation to make it work correctly. Any questions on any of that there? Okay, so we talked about punching it in correctly. We didn't do any sort of examples, so why don't we do a couple here just to make sure everybody knows how to properly punch these guys in. So let's do 7.5 times 10 to the minus 3 divided by 6.9 times 10 to the 16. And let's do 2.5 times 10 to the minus 4 times 7.8 times 10 to the 18. All right, see what you get in there. Make sure you use your exponent button. Again, you should not be using any multiplication button. Should not be using any shift or second and log button. None of those buttons. Okay, let's take a look. So if I was going to punch the first one in, again, I would go 7.5. I would hit my exponent button. And then I would do my negative button and 3. And they would look probably something like this on my calculator or something like this. Actually looks something like that. Then I'm going to hit, obviously, my not multiplication. I'm going to hit my division button, and then I'm going to go 6.9. Once again, exponent button. This is a positive exponent, so I just need to hit 16. And again, it should probably look something like this on your display, or maybe like this. And then obviously hit equals. And if I do all that good stuff there, 7.5 exponent minus 3. It's going to give me something like, we'll do a little rounding here, 1.1 times 10 to the minus 19. On my calculator, by the way, it's something like 1.08695652. E minus 19. Couple things people screw up on. First off, they forget the exponent part when they give the answer. So that E again represents the times 10 part. And when you write it as a number for an answer, you should write the times 10 part. You should not write the E part. So do not write the answer as 1.1 E minus 19. Write it as times 10 to the minus 19. Any questions on that one there? All right, looking at the second one, same deal. We're going to go 2.5. We're going to hit our exponent button, going to hit our negative button and 4. We're going to times it by 7.8, exponent button and 18, hit equals. And I'll do a little rounding on here. On the calculator, it's 1.95 times 10 to the 15, which might round something like 2.0 times 10 to the 15. We'll talk about why we round in a little bit here in this chapter, but more importantly here, the answer that you get is more important at this point. Any questions on that? Again, if the front part of your number looks good, but that like exponent part's off, it's probably the way you're punching it in. And again, when you do write it, do not use the E. All right. So more importantly, sometimes than writing things in scientific notation is to know how to actually punch it into your calculator is sometimes a lot more important. You do not, as I mentioned, I think last time, need to give every answer in scientific notation unless it asks you to do so. If you want to, you can. And as we talked about last time, there may be only one way for you to get the answer correctly in terms of significant figures, and that is to write in scientific notation. And that is because we talked about last time, all the numbers in front of the times 10 part are significant. So those are all sig figs. That means this number here, the way it's written, has two significant figures. So any number before the times 10 part in scientific notation is always significant. The way I wrote it, you know, when I wrote it up here, this number written like this would have three significant figures. Again, all those would be significant. So you could kind of really control how many significant figures you want to put on a number by writing it in scientific notation, which is why in certain cases, it's the only way to get it to the right number of significant figures. Any questions? Can you do it without a calculator? You can, but there's gonna be a lot of numbers you're gonna probably be a little bit hard to kind of do, but you can add the exponents, divide, you know, and those types, subtract them depending on what operation you're doing, but much easier to use the calculator in most calculuses, yeah. In addition to that, remember that your calculator may not give you your answer in scientific notation, right? Unless you have a program to do so. Sometimes they will give you your answer in scientific notation. Sometimes they'll just give it to you in decimal form. And again, it's fine. And sometimes when you put a number in scientific notation in your calculator, it will change it to a decimal. And sometimes it will not. And it will not do it in situations where it doesn't have enough places to put all the zeros, and places where it can, it usually will change it into a decimal. So keep that in mind. All right. So looking at some examples as we talked about here in terms of turning numbers into scientific notation. We take this guy, we want to move the decimal point 1 and 2 places to the left. That's going to give us 5.68762 times 10 to the 2 is where I moved it. If we go here, we got to go 1 place, 2 places, 3 places, 4 places, 5 places, and 6 places to get to a number between 1 and 10. And that's going to give me 7.72 times 10 to the minus 6. Here we will go 1 place, 2 places, 3 places, and 4 places. Gives us 1.25 times 10 to the 4th. And lastly, here we would go just 1 place. And that'll give us 1.35 times 10 to the minus 1. Any questions on how to turn those into scientific notation? We will talk about a little bit later on in this chapter why in certain cases we keep all the numbers, and in certain cases we get rid of zeros, like we have here. And the real reason is significant figures. So whenever you write a number from, say, decimal form to scientific notation, or go from scientific notation to decimal, you should not lose any significant figures. The top number there, actually, all those numbers in the top number are significant, which is why we kept them all as we go to the other side. And in the case down here, as we'll talk about, only the 1, 2, and 5 are significant, which is why we dropped the zeros in that case. So you want to make sure that you maintain the proper number of significant figures, regardless of sort of which way you're going. We'll talk about how to count those a little bit later on. Obviously here, in this case, only these are significant. So that would give us 4.25 times 10. And again, we would go 1, 2, 3, 4, 5 places. And only the 8 is actually significant here. So 1, 2, 3, 4, 5, 6, 7 places. Minus 7. We also talked about, I think last time, larger positive exponents, bigger numbers, negative exponents, smaller numbers, right? All right. So once again, you obviously need to be able to write scientific notation, turn scientific notation into a decimal, and more important than all that for most of the chapters is, as we were talking about, basically being able to punch it into your calculator. So we're talking a little bit about sig figs and scientific notation and what's important. Let's talk a little bit about measurements and how to properly take measurements. So there is uncertainty in any measurement that you make. So any measurement that you take, no matter what it is, there's always some degree of uncertainty that will happen. The degree of uncertainty is really based on the piece of equipment that you use to take that measurement. So it's always important when you use a piece of equipment, whatever it may be, that you actually look at the scale that's written on the piece of equipment so you know how to properly take the measurement, how far you should take the measurement, and ultimately you'll know how many significant figures your measurement should have. So let's take a look at a ruler. So let's call this 1, we'll call that 2, we'll close our ruler-ish. All these centimeters here. And if we wanted to measure, say, something like that. All right, so whenever you use any piece of equipment, like a ruler, a piece of glassware, there's usually 2 types of markings that you could see on the glassware or ruler or whatever you're looking at. There's usually larger markings, and there's usually kind of smaller markings. So on this particular one here, the larger marking, one of them is 1, the other one is 2. So between each large marking, that is a difference of 1 centimeter. Now we also want to figure out on this piece of equipment, what does the smaller markings represent? So we want to count the smaller markings, and it's important that you actually count sort of correctly. So usually speaking, you start at the marking past the last large marking, and you go to the next large marking. So we would actually start counting right here. That would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we're going to go past the first large marking, stop on the next large marking. So there are 10 markings in between 1 centimeter. That means each of the small markings represents how much? Yeah, so it represents 0.1 of a centimeter, right there. And that would be 1.1, 1.2, 1.3, 1.4, 1.5, 1.6, 1.7, 1.8, 1.9, and 2. So when we take an actual measurement, there should always be numbers that pretty much no matter who takes a peek at it, everybody should agree that it is at least this amount of the measurement. So looking at my red line there, everybody should agree it is at least 1.5 in that case. And these are sometimes referred to as these certain numbers. And the estimation does come into play at this point because we can see that it's not exactly at 1.5. It's not exactly at 1.6. So we got to kind of make an estimate. Now, I may look at that and go, well, I think it's maybe like dead half between both of those markings. So I may call it a 5 and record this along with our unit. And this is our first uncertain digit, or sometimes referred to as the estimated digit. And in this particular case, when you take a measurement and you record all the certain numbers plus the first uncertain number, this is what is referred to as significant figures, really. That means that this particular measurement has how many significant figures? It has 3 significant figures. Usually speaking, that last digit is like plus or minus 1. Yeah. So what we're saying in this measurement is, I think it is 1.55. Well, maybe it's like 1.56, 1.54, which if you kind of look at where it's sitting, It's pretty reasonable as to, based on that scale, sort of where it is sitting. Any questions on that there? Now, we can take the smallest markings and divide it by 2. So if we take the smallest marking and we divide it by 2, that will give us 0.05 centimeters. And this is sometimes referred to as sort of the precision of the instrument. We could take this reading to plus or minus 0.05. So sometimes this is written 1.55 centimeters plus or minus 0.05 centimeters. Really, what it will tell you is that is 2 decimal places. That is how far you should take that reading to. You should take it to 2 decimal places. In general, you could go usually 1 more place to the right of the smallest marking. So our smallest marking here was 0.1. We could actually take the reading 1 more place to the right of that, which in this case is to the 2nd decimal place. Any questions on that there? Yeah. Yeah, anything that you use to measure should have a scale, and you really do have to look at it and figure out what the scale really means. And it could even vary. You could even, for example, in lab, depending on who they bought the glassware from, you both could be using your same 10 milliliter graduated cylinder, and it could have a slightly different sort of scaling depending on who made it and stuff like that. So it's really important to always look at the one place where you really don't have to worry about sort of figuring out, how far you should take the reading to is anything that's digital. So like a digital, like the balances in the lab, those scales, anything that's digital, you pretty much just record all the numbers because they're important. Otherwise they wouldn't be there. But anything that has lines and markings, you really have to look at those 2 things. What does the large markings represent? What does the small markings represent? And how far you could really take that reading to. And again, usually it's 1 more place to the right of the smallest marking, or you can figure it out by just taking the smallest marking and divide by 2, and that's how far you should take it to. Other questions? So let's take a look at if we had, say, some type of volume situation. About 20, call these milliliters. We'll put some volume of something in there maybe. There. Now, whenever we put a liquid into, say, a glass container, we typically will see the curvature of the liquid. Probably not that dramatic, but some type of curvature of the liquid. Basically, this is what is known as the meniscus. And we usually always read from the bottom of the meniscus is where you want to take the reading from. The real reason is what is happening here, we'll talk a little bit about it in a later chapter, is the attractive forces between the liquid and the glass are stronger than the attractive forces between the liquid and itself. So what happens on the side where the liquid is in contact with the glass, the capillary action, it starts to rise up the side because they're much more attracted to it. And that's why we read from the bottom of the meniscus, because without that attraction, the real volume is down there at the bottom. So that's why we always sort of read from the bottom meniscus. Most substances will do this sort of U meniscus. There are certain substances that can kind of go the other way that have actually a much stronger attraction to itself than the glass. You don't see it too much anymore because they take it out of all the labs, but like mercury. Mercury actually goes the opposite way. The kind of curve goes upwards like an N. And in that case, you would actually read from the top of the meniscus because the opposite effect is happening. But 9 times out of 10, you'll see this kind of U sort of meniscus. Always read from the bottom, unless you got something like mercury and stuff like that. So here we still want to kind of do the same thing we did before. I got big markings at 10 and 20, which means my large markings here represents 10 milliliters. I once again want to count how many of the small markings there are between those large markings. So again, starting to count here, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Here we have 10 markings between 10 milliliters. In this particular case, that means each of the smallest markings represents how much? 1 milliliter is the small markings. That is 11, that is 12, that is 13, that is 14, 15, 16, 17, and so forth. So once again here, we would look for our meniscus. And depending on the piece of glassware you're using, sometimes it's easier to see than others. If you're using like a beaker that has a really wide opening, it's going to be pretty spread out. If you're using more of a graduated cylinder, you'll be able to kind of see it a little bit better. When we look at this, everybody should agree it is at least 15. Once again here, we are not exactly at 15, not exactly at 16. So some degree of estimate has to happen here. Maybe I think it's closer to 16 than 15 in this case. So maybe I record like a 7. This would be my uncertain, this would be my certain numbers. This would be my first uncertain number. And I should obviously put milliliters here. That would mean this number has how many significant figures? 3 significant figures. The uncertain number here is the 7. Yeah, so maybe it is like 15.8, 15.6, but it's somewhere in that ballpark as we could read it. Once again here, smallest marking whole number, we're able to take it one more place to the right. And if we took the whole number here, 1, and divided it by 2, that gives us plus or minus 0.5 milliliters. So you could write 15.7 milliliters plus or minus 0.5 milliliters, 1 decimal place for our correct reading in this case. Any questions on that there? Like I said before, you may even be using kind of like the same piece of equipment, but made by different people. So they may have different scales. So if I took something, say like this, again, if these are milliliters, we'll do our little meniscus right there. So now when we look at this piece of equipment here, whatever my bad drawing represents, our large number, again, is 10 and 20, which means my large measurement is 10 milliliters. When I look at my small marking in this case, I got 1, 2, 3, 4, and 5 in this case. That means each of the markings represents how much? 2 milliliters here. That would make that like 12, 14, 16, 18. So now when I go to take my reading on this particular scale, I am now between 14 and 16. What comes between 14 and 16? It is 15. So in this particular case, the reading would be 15 is the best that you could do on this particular scale. That is because between 14 and 16, there's no way to know where 14 ends, 15 begins. There's not enough room to sort of visually break it up. So the best that you could do here, this number would have how many significant figures? It would have 2 significant figures. The uncertain number here would be the 5, right? Would be our uncertain. So we're saying, it could be 15, maybe it's 16, maybe it's 14. We could do the same thing here. If I take my smallest markings divided by 2, that means I should do plus or minus 1 milliliter. This also shows the difference between different scaling. A much better sort of volume measurement would be using the one on the left, right? You could take it to the first decimal place. A worse sort of measurement would be using the one on the right there. Any questions on any of that there? Okay. So let's talk about a couple other things here. We'll steal this ruler here, give it a go again. All right, let's say I wanted to measure. Yeah, we'll go with like this guy right about here. Let's say we want to measure that guy and it's like dead on the marking there. So it's dead on 1.4, which gives me a couple of things I could record. I could record 1.4 centimeters, record 1.40 centimeters, 1.400000 centimeters. That is like way too many zeros, by the way. Just don't add extra zeros just to make it more scientific-y. All right. So is there a difference between 1.4 and 1.40? The answer is there is actually a difference between them. So let's take a look at each of these so we can kind of see the difference. When I look at 1.4 written like this means that it has how many significant figures? It does have 2 significant figures. The uncertain digit is which one? It is the 4. So when you record 1.4 centimeters, that is basically saying I think it could be 1.5. Maybe it's like 1.3 with that plus or minus on that last digit. And we could clearly see from our scale here that that guy is nowhere near either of those numbers, right? That's a pretty big area of error between those two digits. Now, if I record 1.40 centimeters, that has how many significant figures? It does have 3 significant figures. The uncertain number is the 0 here at the end. And that's basically saying, I think it's 1.4, but maybe it's like 1.41, maybe it's 1.39, which clearly, if we look at the scaling here, that is pretty much more accurate as to what we're seeing. So sometimes people think it's okay. Yeah, doesn't really matter, right? I could just lop off a 0 here or there. And what you're really doing is making that a much crappier measurement than it should be. There's a lot more error you're putting into that measurement that should not be there based on the equipment that you're doing. So if something hits dead on a number, a marking, you still need to preserve how far you should take that reading based on the equipment. So here still, we know we should always, in this case, take it to 2 decimal places. So that is why we need to put the 0 in there to maintain the 2 decimal places and really maintain the significant figures and how good of a measurement is. So I would highly recommend you do not lop off numbers. Yes, happens a lot when things are dead on a little marking. Also happens a lot with digital equipment. People like, yeah, it's 52.659. 52 sounds good, right? Again, you're losing a lot of significant figures when you do that. Any questions on that? By the way, you should not add numbers, right? There are either too many of them if you don't need to. So sometimes you may need to add a 0 to maintain the proper number of significant figures based on the equipment. Otherwise, again, you're really just stinking up your measurement pretty bad. Any questions on that? All right, let's take a look at some examples here. Actually, let's also talk about another important aspect of measurements. And when we do take measurements, which is accuracy versus precision. And sometimes people use these words sort of interchangeable, but there is a difference between accuracy and precision. Accuracy basically tells you how close your number is to the correct value, the true value. And precision tells you how close a set of numbers are to themselves. So how close a set of numbers sort of agree with each other versus accuracy or being accurate, which is how close you are to what you should be shooting for. So we'll do the classic example of throwing darts at a bullseye. The goal is to hit the bullseye in the middle. So if I take my darts and I throw them, and I throw one here, I throw one here. All right, so I missed the board. It happens. Am I very accurate? I am not, right? Trying to get the bullseye. Am I very precise? That is not good. So I'm going to go double or nothing. So we're not accurate or precise in that case. We're going to throw them again. I go here, here, and here, 3 of them. Am I accurate? I am not accurate. Am I precise? I am. I'm precisely not accurate. You can be very precise and not very accurate. You could screw up and do it. Yes. Wrong every time the same way. And you'll be very, very precise, but not very accurate, which obviously you would not want to do, hopefully. So we go triple or nothing here in a friendly non-wager type of thing. And we take our darts and we toss them and we hit here, here, and here. Am I accurate? And am I precise? I am. And obviously in chemistry and science, you want to be both accurate and you also want to be precise. And that's why a lot of times when we do experiments, right, we do multiple trials to see how reproducible something is. So that is usually what you look at when you look at precision, is how reproducible it is. Can you do it and get the sort of same answer every time? And you also want to be very accurate when you do it. Yeah. Yeah. Yeah, so for example, we'll just do like a basic sort of thing. For say you were trying to figure out the density of a liquid or something, like you will do like an experiment 3, I think. And let's just say the density of that liquid was like 2 grams per milliliter or something, right? So you do the experiment like 4 times, right? And all 4 times you hit like 1.99, 2.01, 2, and all those type of things. You're very accurate, right? Because you hit close to the right number when you calculated the density or figured it out from the experiment. You're also very precise, right? Because all your sort of guys there was in the 2 range, basically, if you calculated it. Now, let's say we did the same thing where we're shooting for 2 grams per milliliter as our density, and you did like 4 trials, and maybe you got like, maybe you got like 8, 8, and like 4 and 4. So maybe it averages out, okay. So maybe you could be accurate, but probably not. But you're all over the place. So you got like 4, 8, 10, 12, and you're not very precise either. So that's sort of what you're looking at. And what we look at in terms of experiments, usually for both of these things, is maybe you've heard of percent error. So percent error is oftentimes what we calculate when we do an experiment. And usually you want a really low percent error. That means basically that you're very close to the true value, whatever that true value may be. It may be like a table value, something you look up and stuff like that. In terms of precision, when we do multiple trials, we often look at something like deviation, like standard deviation, percent deviation, something like that, to see, all these trials that we do, are they reproducible is basically what that tells you, if you can have a very low sort of deviation. Other questions? All right, so that's what we just looked at there. Nice darts. And obviously, as we talked about, you do want to try to do both, be both accurate and precise. And that does come with taking proper readings when you take measurements, depending on the piece of glassware. Because every time you screw up on taking a measurement, you are really kind of screwing up both probably on your accuracy and your precision as you go through it. So you want to make sure that you take those readings correctly. All right, so take a moment here based on the scaling. The big numbers go with the big lines next to them. What is the proper measurement of the blue line that you got going on there? Okay, so once again, we want to look at our big markings. So we got basically a 2 and a 3 there. So our large marking going to be 1 milliliter. Counting our smaller markings like we were doing, we're going to really start past there. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So in this case, we do have 10 markings, which means each of the smaller markings represents 0.1 milliliters. We could do our little division by 2 to really figure out how far we should take the reading. That will give us a plus or minus 0.05. So if this is multiple choice like it is, it pretty much will get rid of everybody about the right answer in this case. But let's go through it here. That is going to be 2.5 right there. That would be 2.6. And this little guy right here would be 2.7. So it definitely is 2.6. That's our certain numbers. We know that we can go one more place to the right of that in this case based on this. And we'll take an estimate. So it's pretty close to that 7. So it looks like they went with 9. And we'll put that there in our plus or minus 0.05 milliliters. So that's going to be D, it looks like, in that particular case. Any questions on that? This number has 3 significant figures. Again, the uncertain digit there being the 9 in this particular case. Let's take a look at another one here. What would the red line? All right, so looking at this, once again, big number difference going to be our 1 centimeter. We again will have basically 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings, which is going to give us our small marking of 0.1 centimeter. In this case, our certain number is definitely 9. It's definitely not 9.1. So once again, we can use our dividing by 2 here to help us out. That's going to give us a plus or minus 0.5 centimeters. So we do need to go to 2 decimal places in this case, which in this case eliminates all of these questions, but just in case it's not a multiple choice question, we definitely need to record 9. We would not record the 0.1 because it's definitely not there yet, right? So we got to figure out kind of where we're at, and it looks like it's just past that 9. So that is why they went with 0.02 centimeters plus or minus 0.05 centimeter. Again, 3 significant figures, the uncertain digit being that 2 at the end of that question on that. Remember that it's important to remember that the uncertain digit, which is sometimes referred to as the estimated digit, is not always the last one written, but it is always the last significant figure that is there. So the last significant figure is always where the estimated digit is. A lot of times that is the last number written, but it's not always the last number that is written in a number. So let's take a look at some other types of measuring devices. As we talked about here, this is a graduated cylinder, and we would want to look at our meniscus and do our reading the same way. In this case, we have 30 and we have 40 in this case. So we have that 10 milliliter spread for our large numbers. There are 10 dashes if we count this way and up. And that means that each of the small markings in this case is 1 milliliter. This being about 35 there, that guy being 36, and this guy above it being 37. So right where we're at is 36, which is our certain numbers. Again, it's kind of close there to the 37, so they went with 0.8, but you could really estimate any digit you want there, which will get us 0.8. And once again, if we were to divide our small digit by 2, that tells us we should go plus or minus 0.5 milliliters, which tells us we should go to 1 decimal place, which is what this reading is here. Uncertain or estimated digit being that 8 at the end of the measurement. Any question on that one there? So graduated cylinder is probably one of the best pieces of equipment that you could use to make volume measurements, to measure out a certain amount of volume. A pretty crappy one to use is a beaker. If you look at beakers, or when you look at your beakers, there's like maybe 3 markings at all, not little markings or anything like that. So you should never, ever really use a beaker to measure out a certain volume of, say, a liquid, unless you want to be way off. So something like a graduated cylinder, which is what this is, has a lot of markings. You can take a pretty good volume reading there and get to the right volume that you're looking for. Another really good thing to sort of use to distribute a certain volume and even really measure in their volume is a burette. And this is a burette, and you use it for titrations, and we'll use it throughout the semester, a little later on in the semester. It is a little different. You actually fill here from the top, put like a funnel on it or something, and it actually will dispense when you open it down here, the liquid out the bottom. So you kind of fill it from the top, you dispense it from the bottom. And what's different about the scaling on a burette is at the very top is 0, and then it increases as you go down in terms of the volume, which means if you have a volume that's sitting right here between the 1 and the 2 marking, that's actually 1 point something, not 2 point something. So it actually increases as you go down. Very common people will read these incorrectly. For example, common volumes for this guy is like 50 milliliters or 25 milliliters. And if you fill it all the way up to the top when you're using a burette, you should always record the actual reading that you see there, which is actually 0, not like 50 or 25. And that's a super common error that people make when they use these things. So when you use a burette, which we use for titrations and some other things, you should always read exactly what the marking says, where the volume is, and you got to remember it does increase as you go downward. So if we kind of look at this guy here, we have 28 here, and we have 29 here. Again, you can see it's increasing as you go down. And that difference of our large marking is 1 milliliter. That means that we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Since I'm counting downwards, 10 right there. And that means that each of the small markings here are going to be 0.1 milliliter. If we divide this by 2, tells us we should take our reading to 2 decimal places there. And that's where we should take our reading to. So if we look at this, once again, 28 here, 28.1, 2, 3, 4, 5, 6, 7, and 8, which is where the 28 comes from. It's not exactly 29, so they went with 0.85. This will have 4, I'm sorry, this will have 4 significant figures, 2 decimal places, the uncertain number here being that 5. So typically speaking, most burettes that you use usually goes to about 2 decimal places is where you should take it. And it's based off of, again, that scaling. So you want to watch out when you use a piece of equipment, how you sort of fill it and how the liquid goes out. So in this case, again, since you kind of fill it from the top, it goes out the bottom. It actually will increase as you go down. So that's one piece of equipment that's a little bit different in terms of how you would sort of look at the scaling. Any questions on that there? All right, so why don't you take a look at this burette and see where you should take the reading on this one. Let's take a look. So once again, this is a burette, which means we are going to fill it from the top. And as it dispenses from the bottom here, it will increase in volume as you go down in the scale. So if we look at a scaling here, we got 20 and we got 30. So once again, our large marking is going to be 10 milliliters. If we count the dots, maybe it's our lines, it may be easier to see up here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 markings between the major units. So that means that we will have each of the smaller markings being 1 milliliter in this particular case. So if we look at our meniscus, it's right about there. And that's right at the 22 marking in this case as it increases going down. What should it recording be here? A, B, C, or D, E?
I said D.
You said D. Anybody else? Yeah. D as well? Okay. So D is the correct one. Again, we know this by dividing this by 2 means that we should take our reading to 0.5 milliliters, which is 1 decimal place. And that is what we see here. The reason we would not go with B is that has only 2 significant figures the way that is written and is not the proper number of digits based off of this piece of equipment. That also has an error in the 2, right? Which means we're saying it's 22, 23, or 21, which is a really big error, which we should not have with this piece of equipment. Obviously, the one on the bottom there, the 22.0, is the 0. That is the uncertain number. And that is where the error is here. Basically saying it's like 22.1 or 21.9, which is pretty close to what it looks like when you look at it. So again here, right on the nose. Make sure that you give it to the proper number of digits. Any questions on how to take readings or anything, measurements? Okay. So clearly, when you do take readings and measurements, you want to always give those measurements to the proper number of digits. And as we talked about, when you do lop off something, if you do, you are making your measurement a lot worse. So now that we talked about sort of where significant figures come from, let's talk about the rules that govern, how we deal with significant figures or how we count significant figures. So the first rule for significant figures is pretty straightforward. Any number that is a non-zero is significant. When you're counting significant figures, it's pretty straightforward. You start left to right in the number, and you don't start counting until you hit the first non-zero. So in the case here, 1, 2, 5, 9, we would start counting at that number. All of those are non-zeros. That would have 4 significant figures when you look at it. Now, the parts for significant figures to give people the hardest time are the zeros. And there's 3 different types of zeros that we deal with. There are leading zeros, and leading zeros are not significant. They're just kind of placeholders. So once again here, we would not start counting until we hit the 4. And that 4 is our first non-zero number. And that is where we would start to count. And that 4 and that 9 is going to be significant. And that would give it 2 significant figures. Now for zeros that find themselves trapped between 2 non-zeros, or sometimes referred to as captive zeros or trapped zeros, those are always going to be significant. So once again, we follow the same rule. We would start counting at the first non-zero on the left, and that is that 5. And then the 2 zeros in the middle would be significant, and the 4 at the end would be significant. So we would have 4 significant figures in that particular number. Probably the zero rule that gives everybody the most difficult time are what are referred to as the trailing zeros. And these are the zeros that come at the end of a number. And these zeros may or may not be significant. And really what determines whether or not the zeros that come at the end of a number are significant is there a decimal point in the number actually written in the number? The decimal point does not need to be near the zeros, just needs to be somewhere in the number. And if there is a decimal point in the number, any zero at the end would be significant. Any zero in a number without a decimal point at the end would be not significant. So when we look at 600 here, written like this has only one significant figure, which is the 6, and that is because there is no decimal point actually written in the number. If we were to write it like this, the second way there, this would now have 3 significant figures. Because of this decimal point, we'll make those guys significant. It would have 3 sig figs. Any question on that there? Yeah. The 600.00, let's add one more for good measure here. How many would it have in this case? It would have 6 significant figures. Yes. These would be significant and those would be significant. Again, the decimal doesn't have to be anywhere near the zeros, as long as they're in the number. It would have 6 significant figures in this case. Now, if you had something like this would have how many significant figures? It would have 2 significant figures, the 1 and the 2. Which one is the uncertain digit or the estimated digit in this case? It is the 2. Yeah. And this is what I was talking about earlier. Those zeros are there to keep the value what it should be, right? 12,000, but they're not significant. So in this case, the uncertain or estimated digit is not the last one written, but it will always be the last significant figure that is written. So I will say 9 times out of 10, it probably is going to be, again, probably the last one written. But in the case that the last zeros or something like that are not significant, it may not be the actually last one that's written. Here, if I wanted, let's say I wanted this number to have 3 significant figures. Can I do that in like decimal form here? Is there a way to get it to 3 significant figures in decimal form? Yeah, in this case, you cannot do it in decimal form. You may be thinking if I did 120, that's 3 significant figures, right? But there is a difference, right, between 120 and 12,000, which is not good. So this is what I also was talking about before. In this case, if we need to give an answer, and this is what popped up on our calculator, but we need to give the answer to 3 significant figures. Really, the only way to get that to 3 significant figures would be, as I heard there, to write it in scientific notation, right? And this would be 1, 2, 3, 4. This would have 3 significant figures. That still keeps it about 12,000, which is the same value. So again, there can be situations where the only way to get it to the right number of significant figures is to write in scientific notation. Any questions on that there? So this number here of 0.000536000320400. If I took a crazy measurement like that, how many significant figures would that have? I don't really know because I just was writing numbers. So let's see together, shall we? All right. So sig figs or not, those numbers right there? No. So this right here, right, is where we should start counting. That's our first non-zero. So that's 1, that's 2, that's 3. All these zeros would count because they're trapped. This would count, that would count, the 0 here would count, the 4 would count, right? How about the zeros at the end? Do they count? The zeros at the end do count because of that decimal point there. So this would be, I have no idea, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 significant figures. Me too. Is it too late for the instructor to update? Is that next week? Might want to leave. All right. So that would have 12. Yeah. They count because there's actually a decimal point in the number. Yeah, it doesn't have to be near them. So it's a very good illustration of the decimal doesn't have to be anywhere near those numbers. So as long as there's a decimal point anywhere in the number, any zeros that end up at the end, and those are the last numbers, the zeros, they will be significant, even if they're not near those decimal points that are there. Question on that? Now, sometimes people think as well, incorrectly, that, you know, hey, these come after the decimal point, these zeros. We don't count those zeros because we have not hit the first non-zero. So you don't start counting until you hit the non-zero. So that's why, even though those zeros technically come after the decimal point, we're not really counting sig figs until we hit the first non-zero. So those are still considered leading zeros at that point. Also, if I wanted to turn this into scientific notation, I don't know why I would want to do that, but I would have to actually keep, technically speaking here, I'm really regretting writing all those zeros now, all of those numbers, because they're all significant in this case, right? So I technically should still have 12 significant figures, and that would be 1, 2, 3, 4 times 10 to the minus 4, right? So if I were to turn that into scientific notation, I got to keep them all because they're all significant. Any questions on counting significant figures? Now let's talk about another type of number that we come across that may not result from a measurement or something like that. And this is really exact numbers. And there's really 2 places or 2 ways that we come across exact numbers. I'll just use these right here. If I wanted to know how many of these pins I have over here on the board, I'm not going to do some type of experiment to figure out how many pins I got. I'm just going to simply count them, right? I would go 2, 4 of them. So any type of number that you get from counting that you wouldn't do any type of measurement or experiment to figure out is considered an exact number. The more common way that we come across exact numbers in chemistry is by what is referred to as definitions. And definitions are considered exact numbers, like this one you should know, as we talked about, I think the other day, 1 inch is 2.54 centimeters exactly. I personally use this one, and they want you to know this one as an exact conversion, so we'll call it that way. I will say some books may not use it as an exact conversion. Some people will use it as 1 pound is 454 grams, but we will use it here in a Saddleback as 1 pound is 453.6 grams, which is an exact conversion. 1 foot is 12 inches. 1 yard is 3 feet. So, you know, these type of things you should maybe know. In addition, things like time, right? There's how many seconds in a minute? Yes, that's 60. How many minutes in an hour? There you go. How many hours in a day? It's 24, not 60, by the way. Yes, people always put that on exams, like 6, because they do like the 60 seconds, 60 minutes, and like 60 hours in a day. So those things obviously won't be provided for sure for you. So you should come with some knowledge, I suppose. But these are also considered exact numbers. And what the deal with exact numbers is this: exact numbers pretty much could have as many significant figures as you want. And what that means is when we do calculations, as we'll talk about, you do want to give your answer to proper number of significant figures. So whenever you come across anything that's considered an exact number, you don't have to worry about it in terms of your calculation. So you could just kind of ignore the sig figs or whatever's going on there. It has no effect on your answer as to how many significant figures your answer should have. Now, there are an exception to that, and it really revolves around the different types of units that we talked about. So if you remember, again, there's English units, there's metric type units. So if you're dealing with anything that is a metric to metric conversion, it's considered an exact number. If you're using anything that's like a English to English conversion, like feet and inches, it's considered an exact number. When you cross over from English to metric, and you're going to use some type of conversion that kind of crosses over between those two sort of units, it is usually not considered an exact number. So usually if you have something like that, you do have to kind of look at the significant figures, except for obviously a couple of those at the top there, which are kind of crossover units. Those are still considered exact numbers. But if you had something, for example, if we didn't use the second one as an exact conversion, but use something like 1 pound is 454 grams instead of 453.6. If you use 454, you then should look at the 454 and the significant figures when you do the calculation. So general rule is if you cross over metric to English and you're doing a bunch of calculations, you do have to kind of take that into account unless it's an exact conversion. And we'll talk more about that, obviously, when we get to those type of calculations. All right. All right, so looking at each of these here, we want to take a second and figure out how many significant figures does each of these have. So take a moment. Okay, let's take a look. So starting at the first one here, we're going to not count until we get there. So all those zeros are not significant. The 3, 0, 4 is, so that's going to be 3 significant figures here, our last part. This is something that's written in scientific notation, which means all those numbers before the times 10 part are going to be significant. So that's going to be 4 significant figures. This is starting counting here, and they're all non-zeros, which means that is going to be 3 significant figures in this case. The 10 here should have what? Should only have 1 significant figure. Again, there is no decimal point written. And here we would not start counting until we hit the 9. This would be significant because it's trapped, and so would the 0 at the end be significant because of the decimal point that's there. That gives us 4 significant figures in this case. Any questions on that? I will also say that sometimes people mess up when they're trying to count significant figures with a number that is written in scientific notation, because they go, oh, that's to the 2, so that goes 1 and 2. So there's only like 3 significant figures. Remember, if I was going to turn this into scientific notation and then go from there to decimal, I would, in this case, because it has 4 significant figures, need to do something like that, yes, to keep it at 4 significant figures. Would I put the 0 after a decimal point? No, because then it would have 5 significant figures. Yeah. So sometimes people mistakenly like take a number that's written in scientific notation, turn it into a decimal, and then count significant figures. You don't need to do that again because all those numbers that come before should be significant. Any questions on any of those there? Okay. All right, so this is measured and exact. So a patient that does weigh 155 pounds, that would obviously be something that you would measure, which means it's got 3 significant figures in that case. a basket holds 8 apples, that definitely is something that you would just count. And that would be more of an exact number, which basically means it could have as many sig figs as you like. 1 kilograms, 1,000 grams, that is a metric to metric conversion, which means it would be an exact number as well. And the distance is about 1,720 kilometers. That would be something that's measured, which in this case means it would have how many significant figures written like that? It would have only 3 significant figures, as that 0 at the end is not going to be significant. I think that's a good place to lay it up.